Welcome back, physics fanatics, or whatever you are, whomever you are. If you have gone through the content on diffraction, the single slit diffraction physics, then this next topic will not be too difficult to extrapolate to, because it is the same idea as wave interference. But what it is a famous experiment done by Thomas Young a long time ago that has serious implications for the wave nature of light. And in any case, it is simply sending light through two slits that are spaced a certain distance apart. We'll call that little d. Distance d from the screen. And so we have, it's kind of like these two slits now are two sources of light, or two sources of waves, kind of like the water wave demo we did, where we had two oscillations going on. One here, little point source beating the water, and over here the same thing. And we get the nodal lines and antinodal lines. Remember that? Well, if light is a wave, we should expect an interference pattern from this situation that's similar to diffraction, although it's going to have some differences. So let's consider the sources here, which is produced from a wavefront coming into this. So here's the two sources, and when they combine here, if it's monochromatic light, then, in other words, the same wavelength, same color, therefore same wavelength, then they should add constructively here. And then, thus, we should have a bright spot right in the center. Now, on the other hand, if the path length differs, remember the pieces of cardboard? The cardboard waves, the two point sources demonstrated as cardboard waves combining at a different point, like this, where it's constructive or destructive, depending on what we're looking for. Well, if the path difference, the length of the path, this one and this one, if the difference between those is a half a wavelength, then we should expect cancellation, destructive interference, and a dark spot. So that would be a dark spot. So let's kind of look at that again. And the difference here is that instead of just having one big opening where we consider, that within this region and the wavefront coming through the whole slit, that we have regions where the wavelength is, the path length differs by a half a wavelength or a full wavelength, and we have the constructive and destructive interference. Destructive and constructive, respectively, actually. But now we have two little slits compared to the entire distance here. And so if you think of these as point sources, they're going to interfere, superimpose on each other, just like what we saw in the wave tank. All right, so we have these two rays, basically, coming from the two slits. And if the path length here is different, we've got angle theta here, which is the same as this angle. All right, if that path difference is lambda over 2, then the hypotenuse, which is d is the hypotenuse of this right triangle here. See the right triangle? Yes, you do. That's a similar triangle as the triangle formed by a line like this. And, well, I'll go to this drawing here, like this, and a straight horizontal back, so to speak. Okay, that wasn't a very good demonstration. Back to what I said a bit ago. It's this angle here, okay? This angle. And those are similar. And they're very skinny triangles, again. Keep that in mind. These are very skinny triangles. If the path length differs by half a wavelength, then we know it's destructive. So d sine of theta is lambda over 2. But if we add another full wavelength to that, then it's the same thing again. Crest meets trough. And so adding another full wavelength to the lambda over 2, you get 3 lambda over 2, 5 lambda over 2, etc. Constructive interference occurs, on the other hand, when the path length differs by whole multiples of the wavelength. So we can write a formula for both situations for the Young's double slit setup. And that is, for constructive interference, d sine of theta, which again is the difference in the path length of the two rays, is m lambda. M is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. At some point, you won't have any additional orders here because the angle will be so big that it just won't work anymore. Kind of like what we saw. Well, it's exactly like we saw with the cardboard demonstration. We only had, depending on circumstances, namely the slit, the whole width, and the frequency of the waves, the wavelength of the waves that were being produced, all that had an impact on how many nodal lines or antinodal lines we would see. So destructive interference occurs when d sine of theta is a half a wavelength, or 3 halves, or 5 halves, and that would be m plus 1/2 lambda. So we have two very similar looking formulas, with m being 0 or any whole number. For constructive, it just sits there like it is. Destructive, m plus 1/2. That's the only difference. M or m plus 1/2. And those are the formulas for getting constructive, destructive interference in a double slit pattern. Our next topic to consider, after we work with this a little bit, do some problems, do a lab, our next step is to consider a diffraction grading, or a whole bunch, not just 2 slits, but very, very, very many slits in some physical device. So we'll look at as our next topic.